Good morning. I'm Richard Watson, and I hope you enjoy what I have to say about our information extraction system for mobile LiDAR survey data. The presentation will start with an overview of our company and also Civil Tech Solutions, which is our partner company. Civil Tech Solutions collects LiDAR data, and our little company is analysing it to make the information more readily available. I'll also be talking about an overview of LiDAR and the LiDAR system called Civil AI, which is a mobile LiDAR system. Then I'll move on to talk about our WebGIS system, which is designed to make the data more readily available to users. I'll briefly touch on the back-end database, which is PostGIS, and the back-end server, which is Fast API. So far, this project is a work in progress, but we have developed a basic front-end user interface, a prototype, to make it clear that we have done something, and it's good for selling the system to potential clients. I will talk about visualisation of LiDAR data and conclude with what we've done so far. My company is a small consulting firm in Melbourne, Ryan Watson Consulting, established in October 2020, based in the eastern suburbs of Melbourne, although our partner company is a long way away in Darwin. We started out doing research with Swinburne University, which is based in Melbourne. Research, initially we were working on Internet of Things, but more recently we've moved into geospatial data analytics and urban digital twin modelling and 2D and 3D imagery analysis. Our website is listed there if you want to have a look at that. Also, I've left a few copies of our company brochure on the table right when you come in if anybody's interested in that. Our partner company, Civil Tech Solutions, was established a few years ago. I'm not quite sure when. It's based in Darwin in the Northern Territory, so it's a long way from us, but we recently entertained the CEO of that company when he was exhibiting at an expo in Melbourne. This company does things like maintenance planning for roadworks, reseals, crack sealing, line marking, asset audits, which is very important for local councils, including signage, guardrails and markings, compliance and reporting, objective network condition evidence. Those are the things that Civil Tech does, and local government is their main client. Currently, Civil Tech has solutions in Western Australia and the Northern Territory, maybe Queensland as well, basically Australia-wide potentially. They've published some information on some websites, which I've listed there if you can read them. So they've done some good work. It's only a very small company. As far as I know, it's only got a CEO and maybe a few interns. So you may or may not know what LiDAR is. Light detection and ranging. It's an active 3D remote sensing method that uses laser light to measure distances and identify reflecting objects. LiDAR systems emit laser pulses and measure the time it takes for the light to bounce back from an object to calculate the distance. This generates a detailed point cloud that is useful for mapping, surveying, environmental monitoring, like forest assessment and navigation systems. There's a paper there on how light laser scanning uses open software and standards, worth reading. Mobile LiDAR is one form of LiDAR. Other forms are aerial LiDAR, even personal carry LiDAR. But we're being concerned with mobile LiDAR, which is based on mounting a mobile survey system on a vehicle, driven on roadway at traffic speed, which can be quite high, 90 km. The main components of of the system are a LiDAR scanner, a 360-degree camera, a global navigation satellite system, and inertial measurement unit. Those subsystems all produce data which has to be integrated. The civil system, which our partner uses, has got an AI suite which does a certain amount of analysis, but we're taking it further with our WebGIS system. This is a photo of his system mounted on a vehicle. So you drive your network. Okay, I won't read all those things out. I've already covered the components of the system, but you can read through that. So it's all very easy. He makes the system available to councils, basically gives it to them, and so that's a good thing for councils because their manual way of collecting data is very expensive. So they get a free system, and they have to pay for the results, but they can collect the data themselves if they want to. This is a bit hard to read, but this is some of the roadway elements that we're interested in. These are just a subset of the elements that were on the previous slide. And maybe it's a bit hard to read, but the slides will be available on the website later on if you want to look into that. It's also a paper in the ISPRS Journal of Photogrammetry and Remote Sensing. Some of those systems are relevant to what we're doing and some are not. For example, moving elements like cars and pedestrians, we're not really interested in those. Traffic elements include traffic signs, traffic lights, road elements. Well, I'm not quite sure whether they're relevant or not. This is just our initial ideas as to what might be relevant. So this is another slide which shows the elements that identify you by the civil AI system. Civil is a mobile LiDAR system developed in the US by a small company called Civil, would you believe, and it's based in Boston. I'm not quite sure how many users there are in Australia, but well, how many providers. I think our partner, Civil Tech Solutions, may be the only one, but it's a really state-of-the-art system, so it's a good system, he thinks, and we think. The AI software that comes with the Civil suite can segment roadway imagery. Lets us index and cluster assets based on their properties. The asset classes might be road, sidewalk, building, or material type, asphalt, brick, or colour, yellow, grey, etc. We're still learning what this system does. I think maybe the software might be proprietary. But the work that we're doing is using open source software. All right. As I said, we're extending the results produced by the Civil LiDAR system using a WebGIS system, which deploys geospatial web applications, which we've chosen to use FAST API as the server, PostGIS database, and cloud technologies, and they ensure a robust, scalable, and efficient system. The back end will include PostGIS and FAST API. The front end development will have mapping libraries like Leaflet, Cesium, and Open Layers. We will, when we move on to production level, we'll be using containerization with Docker and Docker Compose and cloud deployment. Security and performance will all be relevant, and so we'll be looking into that. We haven't really got to that stage yet. If you can read that, this is a overview of our system, our WebGIS system, showing the data sources, the back end and the front end. The data comes from the LiDAR Survey system, and images. So the civil system includes both the LiDAR and images, and their attributes. The back end will have a data pre-processing. I've only listed some of the Python packages there, which will be GeoPandas, GDAL, Rasterio and PDAL. I'll talk about some of that in a minute. The database will be PostGIS, which, as you know, is an extension of PostgreSQL. There may be GeoTIFF files as well. I'm not quite sure how they fit into PostGIS. Maybe they need to be separate. Fast API, we found that to be very useful. Not everybody knows about that. I haven't heard any talks at this conference about Fast API, but it's really the latest thing. It uses a server called UVcorn, and it generates data, or it serves data, and also documentation, which is a useful feature. It auto-documents what you're doing, so that's helpful to people who want to look at the results. The front end, just some of the things that might be done in the front end are maps, charts, tables, and reports. So that's a pretty standard sort of system, but integrating the LiDAR data and the other data can be quite complex. LiDAR has got some pretty difficult features, very large amounts of data, so that requires certain special care. All right, the back end is PostGIS. You probably all know this, or I hope you do. It's an open source extension for PostgreSQL that adds support for geographic objects. It classifies those objects as geometry and geography. There are over 300 functions for processing spatial data. It's indexed with GIST and SPGIS indices. Spatial data is imported from various formats like shapefiles, GeoJSON and CSV. Supports raster data such as elevation and weather data. The back end is Fast API. It's a modern high-performance Python web framework designed to build APIs. It has a speed that matches the AI network loads. It's asynchronous, which I assume you all understand what that means. AI deployment is very, very simple. It auto-generates docs for seamless collaboration, type safety for robust AI pipelines, designed for microservices and scale, and backed by a thriving ecosystem. So it's only been around since about 2018, but from what I can gather, it is really going ahead. We could have used the well-established GeoServer package. In fact, we did use that for a while, and we may still use it. And I noticed from a talk I went to yesterday that there's a lot of new developments in GeoServer, so we might look into that as well. Although Fast API serves us well for our present needs. GeoServer is more complex, and we think it might take people a bit longer to learn. The front-end user interface, which I said we've developed to basically show people that we're doing something, is a prototype infrastructure viewer, which runs over the internet. We've demonstrated to people, just log onto their browser and they can check out these things. You can click on those buttons. This is a button labelled JPG, and that's something you can either get that file from your own system, or you can get it from the server. Text, GeoTIFF, they're some of the things that can be served. This is an example of the Fast API auto documentation. You see that by clicking on the Docs button. I'm not aware that that feature is available in other API packages. So that's something that people should be aware of as a useful feature. WebMap service, I assume most of you are aware of the WebMap service developed by Open Geospatial Consortium. It serves geo-referenced map images over the internet, allowing users to view maps without downloading the underlying data. It's used by in many applications such as GIS software to display dynamic tile-like map images like JPEGs and PNGs from a server. This saves time and money by eliminating the need to download and store large data sets. Going back to our prototype, that's a map viewer. I think that map looks like Victoria, Australia. But there's all sorts of maps there. We're still working on that. In fact, my business partner, Peter Ryan, told me today he'd got this working, so that's good. This is a LiDAR data viewer prototype. This uses Cesium, which you're probably familiar with that for displaying 3D data. So this is just an example of just a snapshot of what can be seen via the LiDAR data viewer. Okay, well, just going into our work to show that we've done some hands-on work with Python. Visualization of LiDAR data. We've done all this. To visualise LiDAR data, you can use tools like ArcGIS Pro, Open3D with Python, or QGIS to render 3D point clouds, analyse attributes and apply filters based on elevation, intensity or returns. I've listed some visualisation techniques there. In fact, I've listed some Python code there too, so if you want to run that code, you will get something that looks like that, if you've got the data that we've got. The visualisation techniques include point cloud rendering, which displays raw LiDAR data in 3D space, and colouring it by elevation, intensity or classification, filtering and segmentation to remove noise or isolate features. For example, ground, vegetation or buildings are features that could be identified. Uses return numbers, that's the LiDAR pulse return numbers or classification codes. That can be done by the AI software, I think. Mesh and surface generation converts point clouds to meshes or digital elevation models or DEMs. That's useful for terrain analysis and 3D modelling. So there's a bit of Python code for you. You can, 5? Okay, I can skip through this. This is just another way of visualising LiDAR data. For raw LiDAR point cloud data, which is often in LAS or LAS formats, you can use libraries like GlassPy to read the data and Matplotlib PyPlot for 2D or Toolkit's mplot 3D for 3D visualisation. There's some Python code there which works and produces something like that. This is another way of visualising LiDAR data with Matplotlib in Python. Typically involves either rasterised LiDAR data like digital elevation models or canopy height models or raw point cloud data. Fourthly, the Python-based package Pottery has been developed by University in Vienna, Austria, Institute of Computer Graphics for web-based visualisation of large point clouds, so it's useful for our WebGIS project. It's free and open source, it's been tested with up to 640 billion points. Features multi-res format with binary LAS or compressed LAS files, high quality rendering, iDome lighting, various point attributes, RGB, intensity classification, measuring, height profiles. I've had a quick look at that, so I'm not fully aware of all it does, but it seems pretty good. All right, conclusions of what I've been saying today. Ryan Watson Consulting and Civil Tech Solutions, our partner, are developing a WebGIS application to make the results of LiDAR surveys of roadway infrastructure more accessible and user-friendly. And this will include the latest LLM and RAG features when we know how to do it, and that we're working on it. We're hoping we'll get some people that know how to do that. This will assist councils and infrastructure suppliers with inventory management, repairs and road safety. As I've said, work is progressing on the application back end using a PostGIS database and fast API server. We've developed a prototype front end to assist in requirements determination. So the front end of the final product might be quite different than what we've developed so far, but we've decided we needed something, and that looks good. So I've come to my end. Okay, so.
Thank you. Thank you very much, Richard. Do we have any questions? Yes.
Yeah, thank you for the presentation. I just want to ask about what are the limitations of the segmentation process? How finely grained can you go? Yeah, how finely grained is the identification of elements? I was thinking when I saw the picture of the stop sign, can you identify a stop sign, or is it just returned as a road sign?
Yeah, yes, I believe so. Yeah, our work hasn't really gone into the civil AI suite. We're just going to get given that. Yeah, so I haven't worked with the details of that, but potentially, I mean, they say that it does, well, it can identify a lot of things, so pretty good. But we're looking at at the various algorithms. As you may know, it's very complex. There's a lot of different algorithms for identifying different features. Yeah, so getting on top of all those algorithms is quite a big ask. Any more questions? No? I think I might have stumped you all. Maybe not. So, have you got any questions? No?
Well, I wanted to ask you, do you have a timeline in mind for how the future of this project will evolve?
Yeah, we're working on that now. We are in the early stages of really moving forward with this project. We've just taken on a data scientist who has got a successful company in Bangladesh, actually, and he's a part-time academic at Swinburne University, and he's really moving us forward. So we've got a timeline. This is all very much things that are happening now. But yeah, you can grab a copy of my brochure, and if anybody wants a copy of we've written a paper as well. I was going to give them out, but I forgot to bring them with me. But that'll be on the website along with these slides, I would think. Thanks.
Thank you very much, Richard.